Yeah, welcome everybody to another one of these sessions on diffusion studies that we've been having, and thank you for joining us. So what we have today is a slightly different sort of a program, and as I've been just talking about this before we went on, that there's a lot of different areas of geosciences where diffusion and the diffusion equation is used, and we, at least us geochemists and petrologists, often tend to focus on the modeling of concentration gradients to get timescales, and we've been looking at a lot of that in the previous talks on experimental measurements of diffusion coefficients and modeling of timescales of different kinds of rocks and mineral systems to using diffusion processes. So that's, geospeedometry or diffusion chronometry or whatever you choose to call those things. Now, as I said, there are many other applications of diffusion in the geosciences, and today we will deal with two quite different applications, but again, just as became clear while we were talking earlier before this thing, there are many other possible areas of applications of diffusion in geosciences, and hopefully in one of our future sessions we'll get to see some of the other applications. But today we have two very distinguished speakers. So David Dobson from the University College London and Shun-ichiro from the University of Yale in the US. So the first speaker will be David Dobson. David is a mineral physicist. He did his PhD in UCL in London in 1996. And then he went to Germany and spent a good bit of time the experimental labs in Bayreuth. And in 2002, he went back to London with a Royal Society fellowship and held that for a while, and eventually moved on to becoming a professor there. He's won several awards, including the Bessel Award, which has allowed him to go back and forth between Bayreuth, Munich, and other places in Germany and London. And he'll speak today about extreme anisotropic diffusion in post-perovskite and implications for diffusion creep. So there are three things that are kind of new and different from the other talks we've been listening to. One, he'll be talking about anisotropy, which we haven't discussed that much usually. Then post-perovskite, that's something that we don't find as a rock on the surface, but we can still use diffusion to study that and know something about it. And diffusion creep is, of course, a mechanical behavior rather than a chemical behavior. And so that's also a new aspect. So we look forward to listening to that. So I forgot what I should have done before is to introduce you to the scheme of the sessions here. So we'll have David's talk and then a few questions on that. Then we'll have Shun speak and a few questions on that. And then we can have a discussion or question on both of these talks together. So with that, I'll just let David take over. All yours, David.
Thank you. Okay, you need to stop screen sharing and then I can
see. Yeah.
There we go. Good. Okay, well, thank you very much, Shumit, for the invitation, and thank you both Shumit and Linda for organizing these. I think they're great seminars. So we're looking at the deep earth today, or I'm looking at the deep earth today. Okay, that's interesting. There we go. So post-perovskite occurs at the D double prime region, within the D double prime region, so right at the base of the Earth's mantle. Let me put my laser pointer on. So down here at the core mantle boundary, in the bottom 200 kilometers or so. And this is just a simulation showing what we can do with numerical simulations these days. The viscosity, this is a convection simulation. The viscosity is assumed to be Newtonian. So there's a stress dependence of 1 on the viscosity, and it's assumed to be isotropic, and it's also assumed to be grain size independent. You can produce things like this. It kind of looks like what we see with seismic imaging, tomographic imaging of the mantle. In order to get plate-like behavior at the top, you have to have non-Newtonian rheology. You actually have to allow strain localization. So you end up with plate-like behavior at the top. But this is where we are with our simulations. And what I'm going to be suggesting today is that, as you might expect, things are much more complex than we see in these simulations. So when we see these and when we see seismic tomographic models that look similar to this, actually the issue is resolution, okay? And it's actually much more complex at the core mantle boundary. And I think it looks more like this. I think it looks more like the crust, and you get a lot of strain localization. And in fact, I like to call the core mantle boundary the anti-crust. It's the other thermal boundary region. And I think a lot of the dynamics is like you see in the crust. So I'm going to be talking about diffusion creep, and the traditional view of diffusion creep is that N is 1, so the stress dependence is 1, is unity. Texture is destroyed, or at least texture isn't produced. There is a grain size dependence on the viscosity, and grain size reduction doesn't occur during diffusion creep because the lattice isn't being damaged. It's not like dislocation creep. The lattice isn't being damaged, so there's no dynamic recrystallization occurring. And I'm going to be suggesting actually that these two parts of the traditional view, that texture is destroyed or not produced, is wrong, and also that grain size reduction does occur in certain conditions when you have diffusion creep. Okay, and it's all associated with this anisotropic diffusion. So if we look at the anisotropy, the S wave anisotropy in the mantle, this is just the ratio of the horizontally polarized shear wave to the vertically polarized shear wave. As you go down through the mantle, you start off with something with a very strong anisotropy in the upper mantle, and in particular in the lithosphere. So this is, we think, olivine preferred orientation. And then through most of the mantle, there's very, very little anisotropy. And we think certainly below 660 kilometers depth in the lower mantle, that's probably because it's deforming in diffusion creep. Temperatures are high, stresses are low, it's deforming in diffusion creep. That seems to be reasonable. And then when you get down into the D double prime region, once again, you get this region where you get quite strong polarization again, with horizontally polarized shear waves propagating faster than vertically polarized shear waves, okay? And the normal view of that is that that means that actually this region is, you have a switch from diffusion creep into dislocation creep. I have some issues with this because, of course, the core mantle boundary is a free slip boundary. You know, there is no, the viscosity of the outer core is 0. So it's a free slip boundary. It's also the hottest region in the Earth. You're the closest to the melting temperature in the Earth down in this region, D double prime. So I think it should be deforming in diffusion creep. So that's enough about the introduction, okay? Let's talk about how you calculate the strength of post-perovskite, because post-perovskite is only stable above 120 gigapascals, so we can't do the experiments. So we have to calculate the chemical diffusivity. We have to assume a creep law, and I'm going to be assuming that it's lattice diffusion creep. And then we calculate the viscosity. So we can calculate chemical diffusivities from ab initio simulations. You can calculate the activation entropies and activation enthalpies for diffusion. You can calculate the numbers of vacancies, at least for intrinsic vacancies, from their formation energies. And it's all relatively simple to do these days, and you can get relatively good answers. So Michael Amann did this back in 2010, and he did it for Pericles. So these are the experimental data that we have. The symbols on all these are experimental data, and the lines are the simulations. So for magnesium ion interdiffusion, and for magnesium self-diffusion and oxygen self-diffusion, you know, across the ranges of pressures and ranges of temperatures where we have data, these are the vacancy concentrations. And these are actually the vacancy concentrations measured in the experiments or defined by the chemistry of the samples in the experiments, which have been used to normalize the vacancy diffusivity from the simulations. And these are the simulation results, and they agree really, really well. So for periclase, it works very well. For perovskite, it works really well. For oxygen diffusion, for magnesium diffusion, for silicon diffusion, it works all really remarkably well, okay, across a range of temperatures, all of the pressures that we have, and across about, 8 orders of magnitude of variation of diffusivity. The worst agreement that we have is about a factor of 3. So it seems to work very well with simulations. So that's fine for perovskite, and we can do it. We can do these simulations across, at whatever pressure we want. So right the way across the lower mantle. And this is the diffusivity that you have along a geotherm for the whole of the lower mantle, except for post-perovskite. So here is perovskite. It's the isotropic. The silicon and the magnesium diffusivities are very similar. The oxygen diffusivity is very high. This is periclase here for oxygen and for magnesium and oxygen. Post-perovskite looks like this. So post-perovskite is extremely anisotropic, with diffusion in the along the A direction being extremely fast. The C direction is very similar to the diffusivity in perovskite, and in the B crystallographic direction, it's extremely slow. And there are 8 orders of magnitude of anisotropy in the post-perovskite simulations. Okay, it's quite nice that in the B direction, it's very similar to perovskite, because actually in the C crystallographic direction, it's similar to perovskite, because actually in the C crystallographic direction, the structures are very, very similar. Okay, and in the B crystallographic direction, that's where post-perovskite is a layered structure. Okay, so we can do those simulations. You can then assume some sort of a grain size and a vacancy concentration. So if we use experimental vacancies, then we need a grain size of about 1 millimeter, and the perovskite then reproduces, this is the blue, the perovskite viscosity, Nabarro Herring diffusion creep viscosity for a 1 millimeter grain size, and the experimental vacancies agrees really rather well with geophysical estimates of the viscosity of the lower mantle. Okay, if we actually assume that the vacancy concentration in the lower mantle is dominated by intrinsic vacancies, and there are very few extrinsic vacancies, you end up with about 100 ppm vacancies. You need a grain size of about 0.1 millimeters. Okay, so that's that. But we have a problem that the post-perovskite is extremely anisotropic. So do we choose the viscosity here, which is for the diffusion along the C direction, which is very similar to perovskite? Do we say that it's actually controlled by the slow diffusion direction, in which case post-perovskite ends up being 4 orders of magnitude stronger than perovskite? Or do we assume that it's dominated by the fast diffusion direction, in which case it ends up being 4 orders of magnitude weaker than perovskite? Okay, this is kind of where we were in 2010 when Michael did these simulations. Okay, so we have a few questions. The first question is this anisotropy genuine? 8 orders of magnitude of anisotropy is an incredibly large amount. It's more than the anisotropy of electrical conductivity in perfect single crystal graphite. Okay, so it's incredibly high. That's typical graphite, you get 4 to 5 orders of magnitude of anisotropy. So it really is incredibly high. And if it is genuine, what are the implications? So since then, I've been doing experiments to try and see whether it is genuine anisotropy, and also trying to work out what the implications are. So first of all, we need to see if we can measure the anisotropy of chemical diffusivity in perovskite structures. And I'm going to very briefly talk about stibnite. So this is a nice needles of stibnite, which is antimony sulfide, and then fluoride post-perovskites as well. Okay, and one of the things that we see for all of the post-perovskite structured materials is that they have needles, and it's just generally found that things with anisotropic chemical diffusivities produce needles, and the needles typically grow in the fast diffusion direction. So this is actually a sodium cobalt fluoride post-perovskite, and the A crystallographic direction, the fast diffusion direction, is in the needle direction. This is stibnite, and the fast diffusion direction in stibnite is in the needle direction. And this is actually a calcium platinate, calcium platinate showing needles as well in the A direction. Okay, so the stibnite structure is related to the post-perovskite structure. It's actually the structure that post-perovskite transforms to if you compress it to even higher pressures. So for magnesium silicate, when you go to about a terabar of pressure, you end up producing the stibnite type structure. And all that happens is that the silicons link across the layer there to produce this crankshaft of silicons. Okay, so it's a related structure. And this is the chemical diffusivity of stibnite. Melting temperature here is at about 600 degrees C or so. And you can see that you have a very strong anisotropy of diffusivity in the C direction, which is actually for the post-perovskite setting, for the calcium iridate setting. That's in the A direction. It's about, what's that, 4 orders of magnitude or so faster than in the slower directions. Okay, but stibnite is a really bad analog material. It's semiconductor. It's a narrow band gap semiconductor. It's extremely brittle. It has perfect cleavage, so it's not easy to do experiments with, and it's not easy to work with. And it's not a good analog for post-perovskite. But at least in a related structure, we see a strong anisotropy. Why is that? So I started working on the fluoride analog systems. So I'm going to be showing you interdiffusion between sodium zinc fluoride and other sodium fluoride perovskites and post-perovskites. And I'm just really interested in the zinc. And we're interested in the zinc end member because it's purely divalent. There's no heterovalency in it. So we don't need to worry about vacancy concentrations as much as we would if we had cobalt or manganese or iron. And it's also very simple to do the ab initio simulations on because there's no magnetism in the cobalt zinc fluoride structure. Okay, it transforms to post-perovskite from perovskite in relatively easy multi-anvil press temperature pressure ranges. So they're relatively easy experiments to do. Okay, so we do just standard diffusion couples. We pre-synthesize the materials. This is in a gold capsule. We then repack it in the new capsule and do the diffusion, as you might expect. We get quite nice data. It fits very well to Boltzmann-Metano analysis, and the zinc is the extrapolation down to, in this case, it's a zinc manganese diffusion couple, and it's the extrapolation down to 0 manganese that we're interested in, so the pure zinc. Okay, and what we see is that we get very nice Arrhenius behavior, nice Arrhenius in temperature, and a very simple activation volume of about 5 cubic centimeters per mole. For 1.6 gigapascal experiments, 6, 10 gigapascal experiments. The 14 gigapascal experiment, the diffusivity is much, much higher than we'd expect from the Arrhenius fit. That's actually because at 14 gigapascals, we're above the transition pressure for both of these systems. So it's transforming to post-perovskite as we're doing the diffusion experiment. And if we pre-transform, if we pre-synthesize post-perovskite rather than perovskite and do diffusion couple experiments at 14 gigapascals, what we get is something up here. So significantly higher chemical diffusivities in the post-perovskite. Okay. We can do ab initio simulations on the system. So this is now ab initio diffusivity predicted calculated for 1073 Kelvin, 0.3 ppm vacancies, which is the calculated intrinsic vacancy concentration. This is for the perovskite. This is for post-perovskite here. And you can see that the calculations, the simulations for post-perovskite suggest it's strongly anisotropic. If you take an isotropic average, the isotropic average will be there. And the experiments for perovskite and for, so this is the extrapolation to 14 gigapascal for the perovskite, and the measured post-perovskite chemical diffusivity for the bulk average chemical diffusivity sits here. So it agrees remarkably well with the simulations. Okay? But that doesn't prove that the anisotropy actually exists. Okay. So what I then did was some single crystal diffusion experiments. So this is the dark material here. This is a single crystal of sodium cobalt post-perovskite. You can see it's quite small. That's a 2 micron scale. So it's only about 10 microns long by 2 microns wide. And this was embedded in sodium zinc fluoride perovskite. Okay, so this is post-perovskite embedded in perovskite. And I made the sample by essentially putting in thin layers of the mixture, packing them down so that all of the post-perovskite needles ended up sitting parallel. The perovskite is isotropic, so it sits there randomly. And it actually transforms to post-perovskite during the experiment. So then we have, when we section it, if we section our capsule, then we can find all of these long axes, which are the A axis. And we don't know whether they're B or C axes, what orientation they are, but we know that they're the radial axis. Okay. And what we see is that in the axial direction, we end up with diffusivities that look like this, diffusion gradients that look like this. And in the radial directions, we end up with diffusion gradients that look like this. So these are plotted on the same scale. The matrix diffusivity in every case is of order 10 to the minus 14 square meters per second, 1 to 2 times 10 to the minus 14. The crystal diffusivity along its axis is 5 times 10 to the minus 14 square meters per second. And radially, it's 10 to the minus 16 to 10 to the minus 17 square meters per second, okay, for this experiment or for this sample. Okay. So we see 3 orders of magnitude or 3.5 orders of magnitude of anisotropy in this case. Okay. And in fact, if you look at a map, a chemical map of the crystals, what you can see is right the way at the edge where you're going into the matrix, it ends up looking slightly hairy. And this is actually post-perovskite crystals that have crystallized and in random orientations, and some of them are pointing away from the large single crystal. And in that case, you get fast diffusion down them. So actually, even in the matrix, you can see the anisotropy of the chemical diffusivity. Okay. So it seems as though we can believe the simulations for both the absolute values and for the anisotropy in post-perovskite diffusion. So those experiments, that single crystal anisotropic diffusion experiment that I did, we saw about 3.5 orders of magnitude maximum anisotropy, and the simulations suggest that we should see up to 4 orders of magnitude of anisotropy. So it's quite a good agreement there. Okay. So now what does that then mean for anisotropic diffusion creep? Those of you who have a geological training will know about quadric sections. This is directly equivalent to the optical indicatrix for polarized light, for the propagation of light through geological crystals. So for a second rank tensor like diffusion, you plot 1 over the square root of the diffusivities to produce the quadric section. Okay, and this is one that's drawn for the diffusion in the A direction is 10 times the diffusion in the C direction. And if you want to know how any particular flux will orient with respect to a chemical potential gradient, you draw the gradient centered on the center of the quadric. You then draw tangent planes to the quadric where the gradient is touching the quadric, and at right angles to that, they're the fluxes that you get. Okay, so if you have a higher diffusivity in a direction, then the fluxes will tend to be towards that direction than towards lower diffusivity directions. So for post-perovskite, for magnesium silicate post-perovskite, the difference between the fastest and the second fastest diffusion has about 4 orders of magnitude. And this is the representation quadric section through that AC plane. Between the fastest and the slowest, you actually have 8 orders of magnitude of anisotropy. I can't draw it narrow enough to make an accurate representation quadric section for that. Okay, so that's saying that all of the fluxes should end up be going in the fastest diffusion direction. Okay, all things being equal. It's kind of a nice graphic way of getting a sense of what might happen. But actually, we want to formalize this. So if we consider a rectangular crystal with stresses normal to the crystal faces and parallel to the crystal axes, so this is our system, and this is the system I'm going to be solving for the rest of the talk, then we can solve for the diffusion creep in that situation. If you have isotropic chemical diffusivities, then this is just Greenwood's solution. And if you were to make the crystal axes all equal to 1, this would just be identical to the Nabarro-Herring equation. Okay, but what you can see is that there's a dependence on the length squared, 1 over the length squared in each of the directions. You increase your crystal size, you reduce the strain rate by the square of the crystal size. Okay. For anisotropic diffusivity, this is what we have for anisotropic chemical diffusivity. We have 3 terms in the A, B, and C direction, and we can apply a Lagrange transform to the coordinate system, which is just the transformed coordinate system normalized to the square root of the chemical diffusivity in that direction. Okay, and in this transformed coordinate system, then the diffusivity is isotropic. Okay, and equation 1 then holds. Okay, so if equation 1 then holds, we can then transform it back to the original, to the real world coordinate system, and this is what we get. So it's very similar, except that now we have this dependence on the diffusivities as well. Okay, so this is the equation that I'm going to be using. It's for that special case of stresses parallel to crystallographic axes. Okay. What we find is that for a really strongly anisotropic diffusivity, the slowest diffusion direction doesn't contribute to the deformation. Okay. We also find that for isotropic grain shapes, it's the second fastest diffusion direction, which is rate limiting, because of course, ultimately, if you're going to be, you can diffuse as fast as you want in the fastest direction, but you have to bring the material from somewhere. And it's faster to bring it from in the second fastest direction than it is in the slowest direction. Okay, so the slowest direction doesn't contribute, and you end up rate limited by the second fastest diffusion direction. And also because of this convolution of the grain shape and the diffusivity, you end up with quite a complex non-linear coupling between the grain shape and the diffusion anisotropy. Okay. So if we just consider an isotropic diffusivity, we're going to deform this grain where sigma 3 is vertical here, sigma 1 is horizontal here. Okay, we end up with something which stretches in the vertical and compresses in the horizontal direction. We'll keep sigma 3 and sigma 1 the same, but now we're going to make the diffusivity much, much faster in this direction out of the plane of the image and much slower horizontally. And what you see is that you end up with deformation in the sigma 2 direction and the sigma 3 direction. And you don't get much deformation in the sigma 1 direction because the diffusivity is just too slow. So you can see that actually you really change things a lot. So if we actually consider the situation for post-perovskite in D double prime, so 120 gigapascals, 4,000 Kelvin. We'll start with initially cubic crystals with stresses normal to the crystallographic axes. So the diffusivities in the A direction are 10 to the minus 16 per second, square meters per second. In the C direction, which is the intermediate direction, they're 10 to the minus 20 square meters per second. So four orders of magnitude difference. And then in the B direction, they're even slower by a further 2 orders of magnitude. Okay, so we've got 4 orders of magnitude of anisotropy between the fastest and the second fastest direction. Okay. So we've got something here, is the second fastest direction, and then this is what would be the viscosity in the fastest direction. But I've told you, if you have isotropic crystals, you're rate limited by the diffusion in the second fastest direction. So we should end up with a viscosity which starts off something like this. So if we put 5 megapascals of differential stress on a 1 millimeter crystal with the properties of that post-perovskite, and we're going to be compressing along the X direction in the fast diffusion direction, okay? Then the strain rate in X starts off somewhere around about 10 to the minus 15 per second or so, okay? What happens actually is that the strain rate goes down. It ends up moving towards 0. So the strain rate is being reduced because you're shortening the crystal in the fast diffusion direction, which means that you're lengthening in the crystal in the second fastest diffusion direction, in the rate limiting direction, okay? So the rate limiting step gets slower because you're lengthening the crystal, okay? So that's fine, you get a slight strain hardening rheology. Let's look what happens if you stretch in the X direction. So you're now stretching in the fastest diffusion direction. That means that in the Z direction, the intermediate diffusion direction, you're making your crystal shorter. So the diffusion in that direction happens faster. It's still rate limiting, but it can get faster. So you end up with a strain weakening rheology. This is the length of the crystal as a function of time. And you can see that as Z gets smaller, as X gets longer, and Z will get commensurately smaller for volume conservation, then you get a significant strain weakening. And in fact, you get strain weakening, and at the very weakest point, you end up with a strain rate which is almost 10 to the minus 14. It's actually slightly over 10 to the minus 14 per second. So you've ended up with an order of magnitude of strain weakening or more, okay? It then, once the X direction becomes sufficiently large, once the crystal becomes sufficiently long in the X direction, that becomes rate limiting. This is now slower than diffusion in the Z direction, then you start to strengthen again, okay? Because that's now diffusion in the X direction is rate limiting rather than diffusion in the Z direction. And that will happen once the length X ratio over Z ratio is greater than the square root of the diffusivity in the X direction divided by the diffusivity in the Z direction, okay? So there was 4 orders of magnitude of anisotropy in diffusivity. So once X becomes 100 times longer than Z, then you'll start to get strain weakening, strengthening again, okay? So that's fine. But is it reasonable for crystals to end up being 100 times longer in their thin direction? And remember, there's not been much deformation in the B direction, in the Y direction, in the slowest diffusion direction. So you end up with crystals at this point where it's straining at its very fastest with an aspect ratio of 100 to 10 to 1, okay, approximately, okay? Well, that's all that says. Strain weakening rheology, and the maximum strain rate is X at 100 Z, okay? When you have diffusion creep, then grains rotate, okay? Grains have to rotate in diffusion creep. And if you have very, very long needles, they're not going to cartwheel over, they're actually going to break up during rotation, during deformation. You're going to get crystal boudinage. And we see this during plastic deformation. This is muscovite mica, which is being broken up by crystal boudinage here. And we see it in superalloys. So in this titanium aluminium vanadium superalloy, which deforms in diffusion creep, you can see that these long needles get broken up during diffusion creep. Okay, so what that means is that although you should in principle get a strain weakening and then strain strengthening, at some point these very, very long crystals become dynamically unstable. They break up and you reset the crystal shape. Basically, X gets shorter. Z doesn't get any longer, but X gets shorter. So you reset it to being more like cubic, and you can allow it to happen repeatedly. So you should end up with grain size reduction by breaking up of these needles and then stretching them again and breaking up and stretching repeatedly. That means also you should end up with runaway strain weakening. Okay. So what do we end up with? We find that post-perovskite chemical diffusivity does have extreme anisotropy. And in fact, there's anisotropy for other physical properties as well. The thermal diffusivity has about 1 order of magnitude of anisotropy in it. It is a remarkable material, post-perovskite, and we could talk about that some other time, maybe. When you take into account the shape change, then the rate limiting process for diffusion creep becomes diffusion in the fastest direction. Okay, once you reach, once you've done more than it was actually about, it's a strain of 10. Once you've got to gamma of 10, then diffusion in the fast direction becomes the rate limiting process. But by then you've already weakened by a factor of 10. Okay, which means that post-perovskite is much weaker than perovskite. You end up with a strain weakening rheology, and also you end up with a lattice preferred orientation because the grain shape itself interacts with the strain field, and needles and flattened materials tend to end up orienting with their long axis in the shear direction and their short axis perpendicular to the shear direction. So you end up with a lattice preferred orientation, and you would end up with complex behavior in D double prime, just like in the crust, because you end up with strain localization, and you end up with a generation of textures. So this, I'm back to my contention that post-perovskite and the D double prime region actually looks like this. You end up with these regions of strong strain localization and also strong preferred orientations just by anisotropic diffusion creep. You don't need dislocation creep in D double prime. And I will call it a day there. Thank you.
Well, thank you, David. That was a very clear talk for, at least for the people who are not used to dealing with creep and deformation on an everyday basis. It was very clearly illustrated. So I think everybody got a lot out of it, and it's a new kind of an idea, sort of in many different ways. So maybe there are questions. If you have questions, you can just unmute yourself and ask something, or write something in the chat. And again, to remind you, we will take a couple of questions and then we'll go to the second talk, and then we'll come back and discuss all of it together. So while we are doing that, Shun has a question. Shun, go ahead.
Oh yeah, nice talk. Yeah, I enjoy it. And
Thank you.
I have 2 different questions. Number one, yeah, it's very interesting. Yeah, unbelievably anisotropic diffusion, and yeah, should cause some anisotropy. But the first question is, that is a theory. And you know various analog materials. Have you done any diffusion creep experiments in analog materials to demonstrate your prediction is true?
This is what I am hoping very much to do, and this is why I started working on stibnite, because we can't do diffusion. We can't do good enough diffusion creep measurements at 10 gigapascals, because we need to go to extremely low stresses. We need to go to very large strains at very low strain rates. So I was hoping to do these things at 1 atmosphere on stibnite.
Yeah.
The problem with stibnite is that it cleaves so well. So I'm just doing experiments now to find out under what conditions I can deform stibnite without it cleaving. And once I have that, then we'll be doing those 1 atmosphere experiments.
Yeah, I'm very curious to see what you find.
Absolutely. Absolutely.
Experiments are fun. You know, we do experiments and always some surprises.
Yeah.
Then you have to think about it. It's a fun. And then another one is a kind of geophysical question. Yeah, if your idea is right, then you would expect to see anisotropy in regions where you expect lots of post-perovskite, which is a low temperature region.
Yeah.
The high temperature region, we may not expect so much. Do you think that geophysically inferred regional variation of anisotropy is consistent?
That's a very good point. Yeah. There are a few things that are yes, in some areas. In fact, let me show you. So yes, we do. But just to caveat on that question, because we end up with a very large strain weakening rheology. So just like in this image I have, the anisotropy might actually be localized onto quite narrow zones. So we might not see those as zones of anisotropy in D double prime. But what we should see them as is as seismic scatterers. And we do see a lot of seismic scatterers, particularly in the cold regions of D double prime. But let me just show you one study of anisotropy. Here we go. So this is James Wookie's anisotropy study, I believe. And Andy Novaki, Sana Kotar, and Miyagi all tried to see how best they could fit this with dislocation creep. Okay, so these are cold regions with quite strong anisotropy. And with dislocation creep, what they find is that the best fitting mechanism here would be slip on 100 in 001 planes. So that is an anisotropy of the A-axis in the slip direction and the C-axis within the slip, within the shear plane, but perpendicular to the slip direction. So that's actually what I would predict for the anisotropy for anisotropic diffusion creep. So here's an example where it does seem to work.
Okay, yeah, thank you.
Thank you, Shun. Are there other questions? Others may think about it. So I'll give you something to think about, David, and then I'll introduce Shun and we'll move to the second talk. And, I was thinking about the effect. Okay, so let me see. There's a question on the chat. Let me take that quickly. So thanks for the great talk, David. I'm wondering, how is the vacancy concentration measured in a mineral? Okay, so let's come back to that one because that's a discussion question. So let's come back to that at the end of it. This is from Shenxiao Xu, and we will take that, Shenxiao, after we come back to the question. So the comment I was going to make, David, was that so from the mechanical point of view, what you're saying is if this were to work, that you'll have a grain size reduction.
Yeah.
But D double prime is also a very chemically active region with strong interaction between the metallic core and the post-perovskite. And if you have chemical reactions, that would promote grain growth. And I was wondering how the interaction between those two plays out. We'd have very interesting coupling between the chemistry trying to cause grain growth and the mechanics trying to cause grain reduction.
Yeah.
So I'll let you think about that while I try to switch to the second talk, and we can come back to this after that. All right, everybody. So the second talk, let me go back to my slide here, is from Shun Karato. And Shun is a professor at the Department of Geology and Geophysics at Yale University. And he's had a very long and distinguished career. Of course, most of you know him through one or other of his works, and I'll try not to go through all of that, but briefly, he got his PhD in geophysics in 1977 at the University of Tokyo. And then he went on to be an assistant professor there for a while. After that, from 1981 to 1985, I think he was a research fellow at ANU in Canberra. And Shun may correct me, I think he worked with Ted Ringwood at the time, who's,
no, Marvin Patterson.
Oh, Marvin Patterson. Okay, yeah, so yeah. I thought you also encountered Marvin Patterson and Ted Ringwood. Okay, so both very big names. Then he came back and spent some time in the University of Colorado, University of Tokyo, before joining the University of Minnesota in 1989, where he was a faculty for a very long time until he moved to Yale University in 2001. And where he's been since then. Now, Shun has won a long list of awards, and it's far too long to try to go over here, but he's got some of the highest awards in various geophysics societies, like the Love Medal of EGU and the Inge Lehmann Medal of AGU. So, and there's a very long list otherwise. So with that, I'll let Shun take over, and he'll be, he is known for his work on mechanical behavior of rocks and mantle materials and so forth. But his talk today is something completely different, neither the mantle nor mechanical behavior. And I look forward to a very different use of diffusion in geosciences. Shun, all yours.
Thank you, thank you. Can I?
You should be able to share screen now.
Okay. Let's see. Yeah. Oops. Let's see. Yeah.
To go to the presentation mode. Yeah, you're okay.
Good. So yeah, today I'm going to talk about something which related to the experiments which we have been conducting in collaboration with the Bochum group. This is very much fun work. Number one, new topic for me, which is, fun. Wait a minute, I need to, that is related to the research is related to the question of why Earth is wet planet. And we have a hypothesis to explain why Earth is a wet planet. I'm going to tell you why it is a problem. And then we started the collaboration with Bochum group. I remember it was 2019 AGU meeting. I had a nice dinner with Schmidt, and I told him, I'm working on this. And then Schmidt said to me, oh, we have a fantastic facility. And then, I started collaboration. And then I'm going to talk about what we are doing this. And I focus on some issues of related to diffusion. I thought nothing to do with diffusion, but diffusion is all very difficult to avoid. Everywhere diffusion is there. So I'm going to discuss a few issues related to diffusion in connection to the question of how did Earth got the water, okay? So outline. I'm going to tell you the source of water on Earth and terrestrial planets are the solar wind. Solar wind contains lots of high energy particles with energy of 1 to 10 kilo electron volt, much higher than bonding energy. And those high energy particles, including hydrogen, penetrates into the solid without much chemical equilibrium. And then during penetration, those particles lose energy and stay inside of the material, and it will be going to be accumulated. And as I'm going to show you, we did show indeed amount of hydrogen you can get by number density of hydrogen you can get by this process is enormous. 10 orders, more than 10 order magnitude higher than what you expect from chemical equilibrium. Those are near surface processes, so therefore very effective when you have a dust, okay? And during those ion implantation, called implantation, the acquisition of hydrogen into the grains, if you look at the data, yeah, you find, oh no, there are some processes of features which needs the diffusion. So I'm going to identify what features require diffusion and then how we can incorporate diffusion into the explaining laboratory observations and other things. Like what we found is, yes, hydrogen goes to olivine, hydrogen goes to quartz, and hydrogen goes to OPX. And what we discovered is that the amount of hydrogen trapped in minerals is extremely sensitive to mineral. Olivine a lot, OPX intermediate, quartz much less. And then we are going to explain this based on diffusion. And whatever it is, in the end, by solar wind implantation, we can get enormous amount of hydrogen in it, okay? And as a result, it is a very good mechanism to explain some of the recent observations. After we started this project, last year and this year, there are few papers published, in fact, showing the evidence for solar wind to hydrate some minerals, including Itokawa sample and some other meteorites. And then after talking about microscopic processes of hydrogen implantation, I'm going to discuss a little bit interesting macroscopic diffusion issue. That is, if you have a lot of tiny dusts, you can easily hydrate the surfaces. But if you calculate density of dust in a solar nebula, it turns out to be very much high. And solar nebula is very thick gas, and therefore solar wind does not penetrate so deep. So in order for hydrating whole solar system, you need something else. And then I'm going to discuss very briefly macroscopic diffusion, diffusion in turbulent, called eddy diffusion. And so this is a kind of slide showing motivation. Classic picture of the planetary formation is there is the sun and then the solar nebula, and everything is chemical equilibrium, okay? Gas and dust are chemical equilibrium, and the equilibrium determines the composition. And then if you make this assumption, there is a very important concept in the planetary formation, namely snow line. Because temperature changes from high near sun to low, you can make ice condensation from the gas only at a position where temperature is low. This is called the snow line. It's corresponding to roughly 170 K. And for solar nebula, it's around 3 AU, 2.7 AU, okay, which is far away from the Earth. And then on the other hand, there is a concept of so-called habitable zone, namely the region in which surface temperature of planet is modest enough to keep liquid water, which is in this range. And the interesting challenge is the habitable zone is within the snow line. So in the habitable zone, yeah, temperature is good enough, but you have no water. So this is a big question. And then there are a few hypotheses proposed, but none of them, to me, looks very convincing. So therefore, I started to speculate the alternative mechanism involving the non-equilibrium processes. not only just gas and dust are chemical equilibrium, but the sun radiates lots of high energy particles as a solar wind. And those are quite large, high energy, and large amount of hydrogen are emitted from the sun. And therefore, there is a chance that some particles in the solar nebula can get hydrogen and other elements from the solar wind. And so that's a speculation. But if this is the case, then we don't care snowline because it's not equilibrium. So you can hydrate many materials very close to the sun. So this might work very good. But given that, you need to do experiments. Okay, to tell you a little more about the details, yeah, the model of solar wind acquisition of the water is stage one, first stage is the solar wind produce lots of high energy hydrogen and other species to the dust. And then we need to know how much hydrogen we may get. And then after that, dust eventually has to get together to form the planets. So during this later stage, there should be some hydrogen loss, and we need to know how hydrogen is lost. And in addition to just worry about hydrogen, we have to also worry about hydrogen to deuterium isotopic ratio, because whenever I tell my colleague, oh yes, I have an interesting hypothesis of solar wind origin of water, then everyone told me, oh Shun, didn't you know the DOH ratio? DOH ratio of those terrestrial planets are not same as the DOH ratio of the sun, so your model is wrong. No. I don't have any good time to discuss details, but our model does predict that during the first stage, DOH ratio increases enormously from the solar wind value. And the also later processes, when hydrogen escapes more than deuterium, we may have a change in DOH ratio as well. Okay. So solar wind is the high energy particles coming from the sun. Then velocity is high, escape velocity of the sun higher than that. So 200, 300, 400 kilometers per second. And solar wind, of course, composition is roughly the same as the sun for obvious reasons. And energy of solar wind is distributed something like that. And mostly the 1 to 10 kilo electron volt region, which is high compared to chemical bonding energy. And so therefore, yeah, the lots of hydrogen. Solar wind is a good source of the hydrogen. But you need to know if we have enough hydrogen. Yeah, yes, indeed. Answer is yes. The flux of solar wind is something like that. And if you have if you calculate how much flux from the sun, and for 1 million years, you have plenty of hydrogen, enough to provide Earth. So if this is not, okay, then I have to stop my study. But then I said, yeah, it's okay. Yeah, solar wind has enough hydrogen. So this is the worthwhile. Okay. And then another interesting thing is solar wind is made of many particles. And the solar wind does not follow the energy equipartition law, the fundamental law for the gas. And the conclusion is solar wind is out of equilibrium. This has an enormous implication for the chemistry of materials trapped by the dust, but I'm not going to do that today. So this is the essence of the solar wind hypothesis. Solar wind comes from the sun, go to the dust, and then hydrates near surface regions. And the question you should ask is, does this process give enough hydrogen or water to make wet planets? And how soon does it take? 1 million years or 100 million years? And yeah, so those are questions. And the quick answer is, yeah, I said earlier, yes, a lot of hydrogen. And very quick, 100 years, you can go saturation, okay? So from this cartoon, you can see what to expect theoretically, what happens in the dust when solar wind radiation comes to the surface. This is what you expect. Solar wind comes from the left, this is the surface, and then penetrate into certain depths where energy of the ion is lost and trapped. Then as you increase the flux more and more, and then this peak increases, then finally go to sort of saturation limit. So this is what you expect. Initially, second, third, fourth. So this is the typical textbook case for ion implantation. So therefore, you can identify a few parameters to characterize a ion implantation. One is the penetration depth. It's called range in the those community, and the saturation limit, and width. This is called the struggling. Okay, so these are the key parameters, and then keep this in mind, and then compare what we find in real material to find out what is normal, what is the anomalous, and what requires some explanation. So I will show you a few results which my student Chin-Ten did with the collaboration of Bochum group, where this is the olivine. They implanted hydrogen with a 10 and 20 keV into olivine for various flux. This is a tiny flux, short time, and then added more. So first point is that initially the depth profile of the concentration follows roughly the cartoon textbook thing predicts in here and there. And then furthermore, more importantly, the penetration depth for 10 keV is around here. But if you go to higher energy, penetration depth increases. This is also consistent with theory. Yes, hydrogen penetrates into olivine and the peak at certain depths, and the penetration depth increases with energy. And interesting thing is, if you increase the flux, profile doesn't grow very simply as a Gaussian shape, or instead, at certain point, if flux is very large, this one is the largest flux, peak becomes broad and it becomes nearly flat, not as textbook shows, but nearly saturated. Okay, so that's a general feature we observe for olivine. We did this for olivine and also pyroxene and quartz. And then surprisingly, we found remarkable differences in the nature of hydrogen implantation among different minerals. Briefly, in case of olivine, you can see peak going, and then nearly getting saturated with the high affluence. The saturation level is around 20%. Remember this, 20 atomic percent of hydrogen there, okay? This is room temperature, and at room temperature, even if the highest water viscosity of like 1 atmospheric pressure, equilibrium hydrogen content is, I think, 10 to the minus 12, 10 to the minus 12, not 10 to the minus 1. So this is far higher than equilibrium hydrogen concentration. So hydrogens are there, not due to some dynamic equilibrium. It's non-equilibrium hydrogen. So that's number one. Number two, the penetration profiles are very different between olivine and quartz. Olivine case, as I mentioned earlier, follows more or less theoretical prediction. But in case of quartz, pattern is pretty much flat. So this is the early stage of implantation, very tiny amount of hydrogen there, and then flat. And then as you increase the flux, adding more and more and more, always profile is nearly flat, and then amount increases and going to saturate at certain level. So this would be saturation level. So between olivine and quartz, two things are different. One, olivine follows Gaussian distribution as predicted by simple theory. In contrast, in case of quartz, more diffuse, flat pattern. And if you look at the saturation limit, that is, if you go to infinite, profile would be something like this, and then you can define how much integrated amount of hydrogen you get by integrating this area. This is called column density, integrated area, that is a hydrogen per unit area. So olivine is largest, and then quartz is much lower, okay? So this is a very remarkable difference, which we like to explain by diffusion. Okay. So in this slide, I summarize some details of the high energy particle implantation into a grain. So number one, the quite often concentration depth profile is not quite clearly Gaussian, but there's a deviation from Gaussian. For instance, if you look at the olivine, this is nearly Gaussian, but here shape get a little bit to the left, near the surface. This is surface, okay? Surface area is getting kind of shorter. So this is a slight deviation from Gaussian. And this trend is strong for, and in case of quartz, this is so strong that the profile is nearly flat. Okay. And another point is, observation is, after a certain time, penetration profile reaches asymptotic profile near saturation, okay? And then you can calculate how much hydrogen you get. Using experimental data and knowing amount of flux from the solar wind, from the sun, you can estimate how much time you need to get saturation for actual solar system. That is about 10 to 100 years, very quick. Okay. And another detail, interesting detail I emphasize is the saturation level is very strongly mineral dependent. Olivine is largest, OPX is second, and quartz is last. Given those little surprising details, we like to understand or explain those details. The first question is, yeah, how can we explain those details? Details looks like related to diffusion, but how could diffusion explain those details, which I'm going to discuss in the next 5 or 10 minutes. And yeah, actually another interesting question is, after a certain time, near surface region is saturated. Saturated with hydrogen with enormously high hydrogen content compared to equilibrium, 12 order magnitude or 11 order magnitude higher than that. After this saturation, if you have enough time and high enough temperature, hydrogen may diffuse into the interior. And the question is how this diffusion might occur. Actually, we don't know the answer yet, but I'm going to discuss this, and then I'd like to hear your opinion. And also another question is, as I'm going to discuss later, if you have a tiny dust, and if dusts are exposed to solar wind, hydration is very quick and easy. However, if you do very simple calculations, you realize like a solar nebula is very thick. It's not clean. And therefore, solar wind cannot go so deep. And so therefore, we need to find out how to explain hydration deeper in the solar nebula. Okay, so these are things which I'm going to discuss. So when you want to invoke diffusion to explain some features, we need to know the diffusion coefficients. This summarizes the known diffusion coefficients of hydrogen in quartz and olivine. And for quartz, crystalline quartz, this is hydrogen diffusion. And amorphous quartz, it's much higher than the crystalline quartz. Olivine, crystalline olivine is this one, but amorphous, I don't think we have it yet. And I think in the bottom, I think Philo is working on this, and it would be nice to have it. And when you look at the temperature in our experiments, room temperature, we are looking at over here. And then you can ask, what kind of diffusion coefficients do we need to explain certain interesting detailed features? And then to address this question, we use a very simple equation for diffusion. The diffusion distance is related to the square root of a diffusion coefficient and time. And yeah, and then you can go to the data, like a quartz. Quartz profile is very flat for like a 200 nanometer. If this flat profile were to be attributed to fast diffusion, then you can ask, oh, how much diffusion coefficient do you need? Answer is you need a 10 to the minus 18 square meter per second. So this is what you need quartz. And then you see the room temperature, 10 to the minus 18 you need. So if quartz is crystalline, you cannot explain this. But if quartz is amorphous, yes, very easy. And yeah, so in case of quartz, yes, amorphous quartz is a probable explanation. And then another very important fact about the quartz is when we did experiments on quartz, hydrogen implantation, we used both amorphous quartz and then crystalline quartz. Then we found results are essentially the same. And then in comparison to diffusion, I conclude that even crystalline quartz changes to amorphous very quickly. This is the kind of thing which is very well known. Quartz is very weak against the high energy particle. So therefore diffusion is fast. However, in case of olivine, diffusion cannot be so large as you can see. And that's explain why hydrogen penetration profile in olivine is not as flat as quartz. However, as we identified, even in olivine, we have a tiny details which might be due to diffusion. And then you can ask what kind of diffusion you need if this tiny behavior were due to diffusion. And then answer is, yes, you have to think first, what kind of length scale? This is the 100 nanometer. So we are now talking about 10 nanometer length scale. And if this were to be explained by diffusion, diffusion coefficient got to be minus 20, okay? And then in solid crystalline olivine, diffusion is about here. So it's too low. So we need the enhanced diffusion by perhaps radiation, but this must be investigated. That is the diffusion of hydrogen in amorphous olivine got to be investigated. I think in Bochum, they have a facility to do that, and then I understand they are working on this. Okay. So now I'd like to discuss the possible model to explain mineral sensitivity of saturation level. Olivine is much higher than quartz. To develop this model, okay, maybe it's too much detail, so I will quickly go to this one. To develop this model, yeah, I assume two things. Two processes control the profile of hydrogen inside of a material. One is the addition of hydrogen from the high energy source, in our case, laboratory source of the hydrogen, high energy hydrogen. In case of solar system, this is the solar wind. And this goes into certain depths of material and then gives hydrogen to a certain amount. which is controlled, shown by C bar. This is the saturation limit. In addition, I assume, because of those observations, I assume that there is a diffusion which tries to bring material from the inside to the outside to reduce the hydrogen concentration. So I parameterize diffusion effect as a minus beta C, proportional to concentration C, and the proportional constant is dependent upon diffusion coefficient. So in this model, the two processes are competing. One is the high energy particle implantation, this effect, and the diffusion effect to reduce the hydrogen out from the sample. And you can solve this for steady state very easily to find out that the steady state solution or concentration is related to saturation concentration linked by a non-dimensional quantity Xi parameter, which is proportional, inversely proportional to diffusion coefficient. Okay, and the for mineral with very slow diffusion, namely large Xi, and then the saturation limit is infinite, asymptotic value of the concentration should agree with saturation limit. In contrast, for mineral with fast diffusion, like a quartz, small Xi, this is proportional to Xi, so therefore smaller than saturation limit. This is the theory, very simple, theory to explain why the olivine and quartz behave differently. So here is some link between solar wind and then hydrogen in the planets and the diffusion. And interesting question I'm asking is, after saturation in a grain, you have a very high concentration surface here, where the concentration exceeds solubility limit by 10 order magnitude. Question I'm asking is, what is the diffusion into the interior? Remember, imagine you have a solar wind still coming. So surface layer is, by definition, boundary condition is, yes, concentration is very high by definition, by solar wind. Then if you wait a long time, diffusion should occur to the inside. And then if diffusion occurs inside, profile would be like this. Then interesting question is, if diffusion is like that, then you would get inside of the grain where concentration far exceeds the solubility limit. I think this should happen, but I'm not quite sure. So we are going to do some experiments to test this hypothesis. If indeed this is true, then you would have enormous amount of hydrogen in the dust. And another thing which we have done a little bit is the what happens when you anneal the samples with hydrogen under the conditions where sample is surrounded by low water viscosity and high temperature. Obvious thing is hydrogen diffused out, but at the same time, in many cases, hydrogen may just go to make precipitation. And if hydrogen goes to precipitates, then these are water-filled bubbles. Then surrounding matrix, olivine, is pretty much low hydrogen content because it's dry environment. As a result, therefore, water does not escape from olivine, which is good to make wet sample. Indeed, the evidence of precipitation formation is known quite a long time. The first one is the ANU work was done when I was there. His PhD, and he deformed olivine at low pressure and high temperature, and then look at the sample and showing, yes, bubbles are there. And even more remarkable example is in my lab, Chin made olivine at 5 GPa, 1100 degrees C, and then 10 hours or something annealing, and took out the sample. Then we saw, wow, sample has so many bubbles. However, very interesting thing is when we took FTIR, we did not see substantial any clear evidence of the free water. in FTIR. Water was invisible in the FTIR. And then, yeah, we looked at the inside of the inclusions. And this is it. This is remarkable. Inside of the inclusions, so this is the inside inclusion. This is like a 5 micron scale. Now it's empty. We draw sample and then look at the inclusions. Amazing thing is, surface of inclusion has a topography with a fraction of micron. And that is why inclusion look like a dark. If it's a dark, FTI infrared beam doesn't go through the bubbles, so you don't see anything. So that is the interesting observation. And then finally, a few minutes talk about the role of eddy diffusion. As I mentioned to you earlier, when you have a planet like this and then empty space, but if you look at the dust before planets are formed, then you can distribute this mass into tiny particles. Then you realize that the number density of particle is so large, of course, depends on the size, and so that this solar nebula is not clean, and therefore solar wind cannot penetrate so deep. And you can do very easy calculation to show that if the dust size is 1 micron, penetration depth is about 1,000 kilometers, which is very short distance compared to the 1 AU. If grain size is 1 centimeter, it's 10% of AU. It depends on size, but still not quite 1 AU. So it's opaque. And then we may say, yeah, oh shoot, solar wind mechanism doesn't work because nebula is so thick. But there is one way to solve this problem. In a solar nebula, yes, it's so thick, solar wind doesn't penetrate, but in a solar nebula, we expect turbulence. When you have a turbulence, and then you can define diffusion coefficients corresponding to macroscopic motion of materials, which is dependent on the sonic velocity and the characteristic length, which is the thickness of the disk. And this is quite large because of macroscopic diffusion. And as a result, you might be able to distribute wet dust deep into the interior of the solar wind. Yeah, and then this is a brief summary of diffusion issue. For macroscopic case, microscopic case, each step is like a jump probability. But the macroscopic case, each step is just a sound velocity, and then you can define the eddy diffusion. So summary is, yeah, high energy particles from the solar wind can penetrate into the mineral grains to hydrate those mineral grains. And once you hydrate mineral surfaces, those ions may diffuse out from the grain, but also diffuse into the grain. And this might provide the interesting, important mechanism to make wet planets. I will stop here. Thank you very much.
Well, thank you, Shun. That was a fascinating run through scales and processes. So, going from really nanometer scales on the surfaces of dusts to looking at eddy diffusion on the scale of the solar nebula. And it was just really interesting to see the different ranges where diffusion can show up and play a role. So I think that's very instructive for all the students who are here to think of the ways you can use diffusion to look at things.
Yeah, diffusion is everywhere, isn't it? Diffusion is everywhere.
Exactly. So as I was chatting with David earlier and said a quiz question I asked, and I'll come back to that, but I'll take questions if anybody has any, just speak up or type something into the chat.
I have a quick question.
Yeah, right.
Yeah, thanks for a great talk, Shun. I agree precipitation could potentially be quite a significant component of the process. But I wonder whether it would actually precipitate as hydrogen gas rather than water, because if you had water, you'd have to provide extra oxygen from somewhere because you're only getting it from the mineral stoichiometry. And we know that helium embrittlement happens in nuclear reactors. So would you get hydrogen embrittlement in these grains?
Yeah, well, yeah, thank you for the question. The quick answer is, in some cases, not always. I showed some kind of perfect crime. Inclusion was there, but inclusion don't show inclusion in FTIR. But in many cases, we can see it by broad peak centered around 3,400.
Yeah.
Then we suspect this is probably H2O. So hydrogen is there, but combined with the oxygen and then make inclusions with the H2O. Maybe it really depends on oxygen fugacity, H2 to H2O ratio. But yeah, some are H2O, some are H2. Yeah.
Interesting to see how much oxygen you can implant as well. So I think. Okay, so I don't know, Liam, you have a question?
Yeah, I do have a question. Thank you for the very interesting talk. This is very much, like you said, a departure from a lot of the more classical models that may invoke some more equilibrium process. I was wondering on your diffusion, when you're talking about diffusion from the irradiated layers or the broken layers in the grains towards the interiors, what diffusion coefficients were you using for the interior? Were you using your higher values? Or were you using the more equilibrium values for the non-destroyed grain?
Okay. When I did very quick calculation, I assumed the diffusion coefficients in perfect crystal.
Okay.
Yeah, and then even that, to saturate whole grain of 1 micron, at room temperature, 1 million years.
1 million years to raise the interior concentrations?
Yeah.
Okay, and then can I follow up? Is that all right? So you also talked about fluid inclusions forming in mineral grains as well. I've seen that explanation provided for SIMS results from some of the chondritic regolith samples. Do you need to have large scale fluid inclusions on the scale of microns like you showed from the experiments that you showed, or could it be very nanometer scale inclusions? And if there is fluid inclusions, why have they not been observed in some of these grains that these SIM samples were conducted on? So I'm thinking, I think I may be thinking of like Itakawa or maybe some of that data. There's SIMS data that gives like 1,000 ppm in some of the olidines, and they speculate that there's potentially fluid inclusions. But as far as I'm aware, it hasn't been demonstrated that there's fluid inclusions in the samples that they analyzed.
Okay, let's see. I'm not quite sure what you're asking, but
right. I guess I'm asking. Do you need like large fluid inclusions for the math to work out to balance out to the large hydrogen concentrations implanted in the center of the grains, or can they be sparser nanometer scale fluid inclusions?
Okay, I think we are talking about what happens when solar wind hydrates grains.
Shun, may I quickly interrupt? So I think what he's pointing, and correct me, Liam, if I'm wrong, what he's talking about is when people measure things with SIMS, including dust from Itokawa and some other meteorite samples, often they find a very high hydrogen contents. And the explanation for that or the suggestion has been that the high hydrogen contents are coming from fluid inclusions, but people don't see fluid inclusions. So what he's asking is, do those fluid inclusions have to be on the scale of micrometers, or can they be even smaller on the scale of nanometers that you wouldn't see, but they would affect the hydrogen analysis?
Can you like balance out that way? Have like a sparse nanometer scale set of fluid inclusions rather than large ones?
So your question is, why do they not see inclusions? And the answer really depends on what technique do they use. Itokawa sample, Daly et al. Didn't use SIMS. They use the atomic probe some tool. So essentially, yeah, they just, I'm not an expert, but it seems it's similar. They don't know hydrogen comes from fluid inclusions or OH. They have no clue.
Right.
They just take tiny amount of sample and then get the gas and then analyze the gas. So in these techniques, they wouldn't see it. If they were to use like FTIR, they would see it. So my answer is because of technique they used, they didn't see it. So from that, we cannot conclude either inclusions are present or not.
Okay.
Yeah, but I can tell you that I don't remember the author and year, but there were a few reports on like helium inclusions in cosmic dusts.
Okay.
Then experimentally, these are reproduced. Yeah.
Okay. Thank you. I find this very interesting. It's
yeah. Well, thank you.
Yeah.
Thank you.
Thank you.
So maybe I'll just add quickly that people have done in very different contexts. People have done experiments with noble gases in diamond anvil cells. And when they quench the samples, they seem to find lower solubility than they should. And one of the explanations or possibilities that have been suggested has also been nanoscale inclusions, that bubbles that you don't see. And so there's a real interest in trying to find ways of recognizing those things if they do exist. That's right.
Yeah.
So are there other questions? So I was going to ask you, sorry, I was going to go back to the chat. I was not looking at the chat. So yes, there are questions. Sorry about that. So I have a question for David. So I have two questions for David. So Shun, we'll come back to you. Let's take David.
Sure.
So the one that we had before already, David, if you want to take that.
Yeah.
So he's wondering how the vacancy concentration is measured in a mineral.
Yeah.
Many ways, but go ahead.
So for the samples that I was talking about in that case, so that was for perovskite and for ferropericlase. The ferropericlases, well, it's all based on chemical analyses. So the ferropericlase, there was a certain amount of ferric ion in the iron, and it's assumed that any Fe3+ is charge balanced by metal vacancies in that case. So you just measure the magnesium concentration, the iron concentration, and the ferric-ferrous ratio for the ferropericlase, and then you have vacancies to charge balance that. So we're assuming that the oxygen concentration is essentially 1. So oxygen vacancies are entirely intrinsic. For the perovskites, there were several things. So for the oxygen diffusion experiments that I showed, which were some of my experiments, I actually had a magnesium silicate perovskite, which I doped with a tiny amount of sodium. So we have 1+ species on a 2+ site on the magnesium site. So that has to be charge balanced by oxygen vacancies. So again, we know the oxygen vacancy concentration just from charge balancing the sodium concentration. And for the magnesium ion into diffusion experiments, once again, we're assuming it from the chemistry. So we're again measuring the ferric-ferrous ratio and the ion magnesium ratios to get the magnesium cation vacancy concentration. So I guess that answers that question.
Mm-hmm. It does, but the question it raises is that in some of your models you were using intrinsic vacancy concentration. What you're describing is not completely intrinsic.
Absolutely. So I glossed over that. So the extrinsic vacancy concentrations that we have from experiments at 25 gigapascals are typically under 1%, but 0.2%, that kind of amount. And which is what we're introducing in our experiments just from the stoichiometry of the crystal. When you get to 120 gigapascals, I suspect we're not going to have 0.2% vacancies. Nature abhors a vacuum, and pressure really abhors a vacuum. These are holes. They don't like it at pressure. So when I was talking about post-perovskite and actually the simulations at high pressure, we calculate the energy for formation for a vacancy. So we take a magnesium out of our crystal structure, we say that it makes an MgO, and we look at the energy of a crystal from ab initio simulation, the energy of a crystal missing a magnesium, comparing which has been produced an MgO, and we look at the energy of that system compared to the perfect crystal. Okay, so we can calculate the formation energy of vacancies, and from that, if we know the pressure and temperature, we can calculate what the intrinsic vacancy concentration is as well. So yeah.
Mm-hmm. Thank you. And then there's a question from Igor Rinos. Congratulations both of you on your talks. Now, Ming Gang has questions for both of you. So because David, I'll let you get a drink. And Shun, for you, the question is the penetration of H in the olivine have some preferred distribution? Does it depend on orientation? Is the question is asked.
Okay. The answer is very, very simple. Yeah, it's not depend on orientation. We did experiments on different orientation, A, B, C, and there's no orientation dependence. The explanation is very simple. It's not orientation dependent because the energy is so high compared to chemical bonding. The high energy hydrogen doesn't care. Yeah, does care only how many nuclei and how many electrons are there. Yeah, so answer is experimentally is demonstrated that ion penetration is independent of orientation.
Mm-hmm. And so he also has a question for David, which is the elongation process of the mineral also controlled by the surface energy difference between the different directions?
That's actually a really good question. So sometimes, yes. So when you just look at the crystallization of a mineral, of a crystal, then that tends to be controlled by kinetic effects, by attachment rates. If you leave it to equilibrate, then you should end up ultimately with a crystal shape which minimizes the total surface energy. When you're in a deformation situation, then this is a non-equilibrium thing. But for something where if you had a relatively isotropic chemical diffusivity, so if you look at, for instance, olivine anisotropic mixtures, when you deform those in diffusion creep, you actually generate a texture, and that's a surface energy minimization process. In the case of the post-perovskite, because the chemical diffusivity is so strongly anisotropic, I suspect that will dominate massively over surface energy considerations. But when you have a relatively isotropic chemical diffusivity, then yes, you can produce shape textures and also ultimately lattice preferred orientations by surface energy minimization. Is it Reed and Cooper who did those diffusion creep, the olivine anisotropic diffusion creep experiments?
But this is where my earlier question comes in, but if you have reaction and growth going on at the same time, that would be heavily affected by the surface energy, and then how they play on each other. I think there could be very interesting nonlinear coupling effects.
It could be, and it could be an explanation why we don't end up with a runaway weakening. Ultimately, what I was showing, that runaway weakening makes D double prime too weak. We have to have a way of stopping that from happening. Mm-hmm. And ultimately, grain growth is the way to deal with that. So.
Mm-hmm. Okay. So
I have one question.
Yeah, go ahead.
To David, in your model, you predicted crystal shape is going to be highly anisotropic because of high anisotropy in diffusion.
Yeah.
But when you develop model, did you include the compatibility issues of many grains. You know, when you deform polycrystal materials, you must satisfy compatibility.
Yeah.
Then I suspect if some grain becomes so elongated, you violate compatibility, isn't it?
Absolutely. So what I showed there was just the analytic solution for a single grain. And you're absolutely right, it does violate compatibility. And that's ultimately why they break, why the grains break. So you end up with too large stresses on the surfaces. And so the grains actually end up fracturing. And so you end up with an anisotropy reduction by grain shape breaking because of the compatibility problems.
Yeah, but as I argued like 10 years ago, if you assume compatibility, then all grain by definition must deform in the same way. So rate controlling diffusion coefficient is different. It's the slowest. No?
Well,
I really like to do experiments to see.
Absolutely, I know. I agree. This is really what I want to do with these experiments. Because one of the things that happens is that when you have fast diffusion orientations within the shared direction, then you get more rapid changes of shape than fast diffusion directions not in the shear direction. And that means that you end up placing large attractions on the surfaces which aren't in that fast diffusion direction. So you get more rapid rotations of those surfaces. So things will tend to evolve to end up having their fast directions in the shear direction. But as you say, until we do the experiments, then I really want to do the experiments. When I find the material, I will do them.
Okay, okay.
Sounds like the perfect thing to try on some analog material.
Absolutely.
Exactly. So Shun, I wanted to get back to one of your questions on, actually, if you could have the slides again, and then.
Okay. Let's see. Yes.
So, and if you go back, I'll tell you when to stop. Yeah, that would do.
Okay.
So, so on the second panel here, so you're suggesting that this may form due to diffusion.
Yeah.
And what that would require is that you're producing something with more corners or more curvature out of something that was initially smoother. And I think that'd be difficult to do with a normal diffusion equation, because that just always smooths things out, doesn't produce more angles and more corners.
You're talking about, I was talking about the this
bulge.
Yeah, and my suggestion is just
I know this is very preliminary.
But the observation is a Gaussian shape changed to asymmetrical shape, and hydrogen seems to be going to the surface, and then I need a little more. So,
all I'm saying is that we might need something more than just a simple diffusion equation.
Oh, I know. Yes. And point. Yes. So I agree with you. But I use this to tell you diffusion is playing some role. Then I made extremely simple model to explain why the saturation limit is so different in quartz and already. Do you think this part is okay?
I don't know. This is
naively obvious, isn't it? Because diffusion is so fast, so from quartz, lots of hydrogen goes out. Yeah,
this is new, and this is all very exciting, and this is something that we need to think through and digest, I think, and write. Equations, I find you always have to write with a pen and paper and then think about it. Otherwise.
Okay. Okay. All right.
Suman, can I ask a question?
Yeah, please, go ahead.
No, this relates to what I asked about in the chat. Whether the surface zone was actually equal in its physical properties compared with the interior part of the grains. the profile you've drawn looks like its diffusion is actually faster towards the surface than it is towards the interior, which implies the surface may be damaged, not have a structure which is the same as the bulk material.
Yeah, that's what I suggest. Yeah, as I discussed, yeah, to explain tiny feature, you need to invoke that the diffusion in olivine in the near surface region is much faster, higher than the plane. Yeah. So in a way, I'm suggesting. Yeah, yeah.
So that would explain the shape of the diffusion profile here.
Yeah.
Or the general, qualitatively.
So yeah, surface is damaged, and that's why. Yeah. Yeah.
Okay.
I mean, the issue there is that in terms of the energy and how much energy it takes to cause damage, and I don't know if Hans Werner is there, he would be the expert to talk about this. You don't expect to produce a lot of damage by the implantation itself, but on the other hand, if you are talking about something with 20 atom% hydrogen, that's, structurally sitting there somewhere. It's not just olivine anymore. So, you're probably looking at something like livenite or I don't know what, because it's a lot of hydrogen.
Yeah, yeah.
But the implantation itself, from what I understand, is not going to cause too much damage, but I don't know. Hans Werner, are you there somewhere to comment on that? Sure. Hans Werner, do you get damage when we do these implantations? So for everybody else here, Hans Werner is a nuclear physicist, so he knows much more about this than all of us do. So
yeah, of course we get damage. And there's also a damage profile which is slightly below the range profile of the ions. So you would expect damage not in the maximum of the profile of the hydrogen, but a little bit more to the surface. Yeah.
So the damage would be concentrated closer to the surface than where the peak is.
Yes. Yes.
Yeah, I know one paper in which they demonstrated damage of olivine by I think helium implantation.
Mm-hmm.
This was an old paper, 2002, by French group. Karato.
Yeah, Patrick Cordier was one of them.
Yeah, Patrick Cordier, yes. Mm-hmm. They demonstrated two things. Actually, when they implanted bombard the olivine by helium, amorphous layer was formed. And also the chemistry changes a lot. Olivine changed to OPX.
Yes.
Yeah, that was a remarkable change. So lots of damage for helium. Mm-hmm. Helium, yeah, probably, I don't remember the energy, but it depends on the energy. Yeah. So answer is yes, in some cases, but the quartz is so weak against radiation. So I think that's why the quartz behavior and olivine behavior is so different.
Mm-hmm. Okay, are there other questions and comments? So people are happy with the answers. And I don't see any questions, so I'll just quickly add the comment I was making to David earlier when we were talking that, it's a common, like a quiz question that one can ask, which is the most used work of Albert Einstein. And, people tend to think, relativity maybe, or the photoelectric effect, because everybody has televisions and things. And the answer, hands down, would be the diffusion equation, because you use that in all of what you've heard. You use that in geomorphology. You use that in modeling the stock exchange. You use that in modeling the migration of people. So it's just, way, way, way more used than anything else and Einstein has done a lot of very well-used work, but diffusion beats everything. And that's also his PhD thesis, by the way.
Yeah, that was PhD, yeah.
Yeah, so his PhD was neither photoelectric effect nor relativity, but diffusion. So, so on that note, I think, thank you everybody for being here. So we'll be back here in a month again. We have two very different talks on monitoring of volcanoes and looking at getting down to the nitty-gritty, looking at errors and uncertainties of diffusion modeling and plagioclase. So the announcement will go out, but in the meantime, keep well, keep healthy, and thank you, Shun and David, for some very exciting things.
Thank you so much. Yeah, thank you so much.
Yeah,
I
thank you.
enjoy. Yeah, David, thank you. Yeah, I enjoy your talk. Yeah, thank you. Bye-bye.
Bye-bye.
Okay.